Hello. Okay, so welcome to part two of this video, of this lecture, of this weekly lecture. So, we're going to talk about more about kinds of forces, the common types of forces, all right? And gonna talk about how we treat free body diagrams when we come across these forces, all right? So, I hope you're ready, and yeah, let's get started. So, and remember, you have to turn in your notes for the video for you to get credit. Okay, so when an object, like a box here, is on the surface of a table, it acts on the table with its weight. All right. So, like my free body diagram and my box acting. So this is my box, and I got my weight. Change color. But why doesn't the box just start, you know, rolling around or, you know, just imbalanced? Why is everything in perfect symmetry? Like why is everything just, why is everything just good? Like, why is the box just not moving? You know? Well, that's because when an object is on a surface, the surface will act on that same object with a force. All right. So like we see here, the box will act on the surface with its weight, but the table will act a force on the box as well, and that force is equal in magnitude to the weight and is called the normal force. All right, the normal force. All right. So so what's the normal force? Okay. What's the normal force? Definition. This is a force that is acted on by the surface on an object that is laying on it. All right. So that's our normal force. So a good thing to know is where the normal force will always point. All right. So I want you to keep this rule in your brain. The normal force will always point perpendicular. It's a vector. It's going to point perpendicular to the surface. So if I have my surface here, all right, my normal force will be very perpendicular to that surface. All right. Normal force is always perpendicular to the surface. Never forget this. Never forget this, all right? And how to do the free body diagram is right here, all right? I have my box on the surface, acting on its weight, and the normal force is just the same vector, but just going in a different direction. So actually, it's very, so if my weight, since my weight is equal to mg, my normal force is going to be equal to minus mg. All right, this is very, very correct to say. All right. So, yeah. Well, let's move on to another force. Friction. Why is it that when I roll a ball on the ground, it eventually stops? Well, it's friction, mate. friction. That's why. That's why. And there are two types. So we got static friction. Static friction, so this is friction that, say, friction that keeps objects stuck. Yeah? Static friction is friction that keeps objects stuck. All right, so I have this drawing right here. I have a person pulling a box, all right, and I have a surface. So let me draw my free body diagram, all right. Let's say I care about the box. I only care about the box. So this is my box. I have my normal force, my weight force in the surface, my weight, and then my normal force. But this person is trying to pull this box to the left. He's trying to pull it to the left, but he's not succeeding at all. It's staying there. It's not moving. So, thus, why is it staying there? Because of static friction. Static friction is not allowing it to move. So what direction do you think static friction points at? Static friction will always point in the direction opposite to where the box will move would move if there was no friction. All right? So I know that's a mouthful. Let me write that somewhere. Left this guy. Okay. Yeah. Okay, fine. So static friction points in the direction where an object would go if there. It points in the direction. Sorry, I've left a very big, important word that just needs to be there. So, okay, in the direction opposite. It's a really important word for that sentence. Opposite, where an object would go if there was no friction. Yes. So, if my person is pulling the box here to his left, but it's not moving, the box would go to the left if there was no friction. But we want to get the static friction vector, so that vector points to the right. All right, that vector points to the right. And our free body diagram is going to look like this. All right, where we have a curly F and a little subscript S, meaning static friction. All right, and that's what it looks like on our free body diagram. All right, so yeah. And then we also have kinetic friction. Kinetic friction is very easy. So this is a friction that opposes motion. All right? So if my sled is moving down a slope, it eventually slows down. That's slowing down because it's moving is due to kinetic friction. So, what direction does it point at? Kinetic friction just points in the direction that opposes motion. So if my sled here was going to the right side, my kinetic friction vector will point to the left. So my Newtonian, my free body diagram, if all I had was kinetic friction, of course I'm on a surface, so I have a weight, I got a normal force, but in the horizontal direction, I have kinetic friction. All right, we'll talk more about these on either soon. We'll talk more about them soon. Now, tension. Tension. What is tension? Well, tension is basically. This is basically so wait, hold on. I just want to make sure you guys know this. This is a contact force. Contact force. All right. And then normal force is also a contact force. Just so you know. Just so you know. All right. So tension. This is a contact force that occurs when a string. All right. This is a contact force that occurs when a string or any flexible connector is pulled. All right. So if I have my rope here and I got my mass, so I'm just tell you what tension always points. Tension, this is the vector T, always points towards the origin of the pull. You can't push so tension is all about ropes, essentially. All right, so if I have my nail there and I have a mass going down, well, my tension vector is going to be there. That's my tension vector. But I also have a mass hanging there, so I'm gonna have a weight vector. Now you might think this is like the normal force, but it's not the normal. It's not like the normal force. They're actually different. They're very different. All right. I see the similarity being that they kind of are similar in the way they cancel out the weight vector, but you see the normal force is acted on by a surface. All right. Tension is acted on by a pull. All right. So that's tension. Okay, moving on. The spring force. Okay, so this is actually for now. This is what we'll suffice with. So when the spring is compressed, all right. When compressed, it will push. It will push. So thus, our free body diagram, our FBD of the box, will look like. So we have, let's say our box on the surface, normal, weight, then our force, our spring force will be that way. Now when it's stretched, the velocity goes the opposite way. So Well, not the velocity, but well, it is the velocity does change direction, so yes, it does go the opposite way. But after a stretch, it pulls. It gets pulled back to kind of where it was. So initially, so if I have my Newtonian, my model right there, we would have a spring force in going towards the left direction on the free body diagram. All right, we're getting to the last one. Drag. So this is a resistive force. Just like friction, all right? A resistive force. Almost exactly like friction. But, so is it the same as friction? No, not exactly the same, all right? So friction is from surfaces. Drag can also be from fluids and air. All right. So I have this diagram here of a leaf dropping from a tree. So basically, that leaf will feel some air resistance. All right. So an example of drag force is air resistance. With a few air resistance going back up. All right. So we have to consider air resistance when solving this problem. But we won't solve this problem right now. So, anyway, where does drag always point at? So drag always points in the direction opposing motion. So you see we have our vector pointing down, our velocity vector, the leaf is going down, but drag is going right up because it has to oppose motion. All right. Then thrust. Okay. Sorry, I'm getting a bit tired. Thrust. What's thrust? Well, this is the exhalation, what was the right word to use in this moment, of heat and gases to propel forward. Yeah. Propel, I guess, forward. Yeah, in some way. So thrust. So yeah, if I have my jet here, I have to exhaust in the back. I gotta release gases and heat in the back to be able to move front. All right, and that front movement is called the thrust. All right, that's the thrust. So yeah, those are some of the forces that we have met. All right, so if my something thrust always points opposite to the direction of the exhalation of gases. Yeah. So, yeah, that's basically the forces we'll be dealing with in this course. Like I said, so far we only have one non-contact force that we're going to deal with, which is weight. But the rest are all contact forces. So we've got the normal force, tension, spring, drag, thrust, friction. And I've just told you how to think about them. And when doing your free body diagrams, they were on the side, that's how they would look. And yeah, it's just a last step. Here's a step-by-step for solving problems with Newton 2. So step one is you gotta identify if the problem involves forces. All right, you can only do this if there are forces. But step two, okay, your free body diagram of the system of interest. All right, so a free body diagram, create a free body diagram, and then on that free body diagram, first list the contact forces, and then put the non-contact forces, and then after that, analyze vertical and horizontal motions independently. And then step four is you gotta finally use Newton 2 to solve the problems. All right. So here's a problem that I think we'll deal with a bit later, maybe in class or something. But yeah, I hope this was a fun lecture. I hope you're excited about this chapter as I am. I hope to see you in class soon. Bye.